Okay, I'm going to talk about how to understand the Jacobian formula, because I think it's kind of unmotivated. So I think it's worth trying to find a quick way to understand what's going on here. So in 1D, I think it makes a lot of sense how to get the Jacobian. So really, we're trying to write dx in terms of du, but we need to compensate for length expansion or contraction by adding that g prime of u if x equals g of u. Really, what's going on here is you look at the quotient dx du. And so this is dg of u divided by du. So this is g prime of u du over du. This is g prime of u. So this is the Jacobian. And you can write that as dx du in that parentheses notation that people like to use for Jacobians. So now let's look at 2D and try to use that quotient method. So dx dy divided by du dv. This will be the Jacobian. Okay, so now we're just going to expand. And so this is d, well, wait, let me back up one sec. Dx, if we write x as a function of uv, we just need to use partial derivatives. So there'll be two terms. You won't just have an x prime, you'll have an x prime in u and an x prime in v. So xu du plus xv dv. So if we substitute this in, this is xu du plus xv dv. Remember, I'm using the notation xu equals dx du to save time. And then times, well, it's just the same thing with y, right? Yu du plus yv dv. All this is going to be divided by du dv. Okay, so because this is a quotient in du dv, I'm going to drop the du squared and dv squared terms, because we want a real number, not something weird like du divided by dv. Okay? So if we drop these terms, we'll end up with just the cross terms. So we have xu. I'm going to just draw arrows to indicate where the cross terms are. So we have xu yv, and then we have du dv plus xv yu. Based on the formula for the Jacobian, we're looking good so far. But the only problem is there's no minus sign. Okay? Well, the trick is now we let dv du, we replace this with minus du dv. Okay? So before I explain why that is, let's just see what we get. So if we look at this formula, xu yv du dv plus xv yu dv du, we now have a minus sign, xv yu du dv, and this is all divided by du dv. We end up with exactly that determinant. That's the desired Jacobian. Okay, so why did we do this? Well, the answer is the cross product. Remember, a cross product is anti-commutative. So if you switch them, you have to add a minus sign. And as it turns out, the cross product is equal to area. It's not equal to area, it's related, it's related to area in a very strong way. Right? Because you'll know that the area of a parallelogram with sides given by these vectors, the area is actually the length of A cross B, the cross product. Right? And this du dv is actually, it represents an infinitesimal area. Okay? So this du dv, you could think of it as like a cross product. So if you have dv du, surely that should be minus a du dv by this logic. The fact that it is an area, and cross products give you areas, but you have to account for the minus sign. Okay. And to see why there's see why you get a minus sign with this area. If these are two planar vectors and this is k hat, this area, it'll be k hat times a cross b. Remember, k hat is the z, and the a and b they align the xy plane, and this is the z-axis essentially. It's a vector pointing along the z-axis. And so if you switch, you have to get a minus sign. Okay? So that's basically the idea of what's going on there. And another way you can think about it is it's a little more mathematical. So a second way. The second way is to just draw a coordinate volume. So if you start off with your vector r, position vector xy, well, what if you increment this by du, so r plus a small change. This is basically the Taylor expansion in du, and you do the same thing in dv. Then we have a natural parallelogram here. I said volume. This should be area. Volume area depends on the dimension. So the area of this parallelogram, this will be dA. Okay, and then to find the area of that parallelogram, it is just it's just what I said before. It's the magnitude of the cross product. So it is A cross B, where this thing is RA, and this one is RB. These are the side lengths. The side vectors, they're not lengths. Okay, so that means it's dr du cross dr dv du dv. Okay, and this determinant, you can find cross products by the determinant, right? So I, j, k. So what is this? This is xu, yu, zu. We're in the plane, so that's 0. This is xv, yv, zv. That's again 0. So the only surviving term with all these zeros is just the k component. So it's just xu, yu, xv, yv. Right, and so that's the determinant that we want. Okay, so you can do something very similar in 3D to find 3D Jacobians. For example, that'll help you. That gives you another way to do spherical coordinates. But I think there are simpler ways to do that, which I talked about earlier. And really, it's just what you do is you add if you want to do 3D, I'm just going to indicate red here. You just make another increment in W. And then you just use the fact that a volume of a parallel pipette, a 3D parallelogram, it's just the scalar triple product, A dot B cross C, right? And so this is, again, a determinant, where this is A1, A2, A3, B1, B2, B3, C1, C2, C3. So this is, again, the Jacobian. If we, again, use partial derivatives for the A, B, and C. So it's really a very similar idea. Honestly, in the applications that I know of, I haven't needed to use explicit Jacobians that often, because I think for rescalings, it's almost unnecessary. You just plug in the right numbers, right? Like if you use d of 2u, that's just 2 du. So you should add an extra 2 if you need to, if you have the u substitution x equals 2u. That's not very complicated. And for rotations, the Jacobian's usually 1. If it's a good rotation, there might be a constant factor if it's like x plus y or x minus y. That's not no. There'll be an extra factor, but usually if it's a good rotation, like something like cosine theta x sine theta y minus cosine theta x sine theta y, if it's a good rotation like that, the Jacobian is just 1, so you won't need to do anything with it. So I would just keep this formula in mind, so that if you see it and you need it, you won't get too surprised. But I don't think you'll need to use this very often, this explicit form. Okay, hope this was clarifying, at least. Thanks for watching.